Symmetric matrices. We have mentioned symmetric matrices before. A n by n matrix A is symmetric if A transpose is the same as A. Symmetric will be abbreviated as sim. Remember in chapter 5 we talked about diagonalizable matrices. For a matrix to be diagonalizable, there are some conditions to satisfy, and there's an algorithm that we can check to see if it's diagonalizable. First we see if it has n eigenvalues, and then we see if the dimension of each eigenspace is equal to the multiplicity of that eigenvalue. It turns out that for symmetric matrices, everything becomes so easy because asymmetric matrices is always diagonalizable. There's nothing to check. There's nothing to verify. Every symmetric matrix is diagonalizable, and that's the main result in this section. It is a very powerful result, but it also requires some work to get there, so be warned. There will be lots of proof in the first part of 6.6. Let's first look at a theorem that will help us to understand how symmetric matrices are different from other matrices. This is one theorem from chapter 5. It says that if we have eigenvectors from different eigenspaces, then when we collect these eigenvectors together, they are always linearly independent. It turns out that for symmetric matrices, more can be said about the eigenvectors. More is true. Suppose A, n by n matrix, is a symmetric, and U and V are two eigenvectors of A corresponding to distinct eigenvalues. So U, V are from different eigenspaces. From earlier results, we know U and V must be linearly independent. But now we have the additional condition that A is symmetric, so we can say more. That is, U and V are not only linearly independent, they are orthogonal. Let's prove the theorem. A is symmetric, U and V are eigenvectors corresponding to different eigenvalues. So let's say AU is lambda U and AV is mu V. This one reads mu. And lambda and mu are not the same. Now let's multiply both sides of the first equation by V transpose and V transpose. And let's observe the left-hand side of this equation. We have not used the condition that A is symmetric yet, so let's use that here. V transpose AU, we can write it as B transpose A transpose U, because A and A transpose are the same. We can rewrite it as AV transpose U. V is eigenvector of A, and AV is equal to mu V. We can plug it in here. So this is the left-hand side, and this is right-hand side. Let's equate them. Left-hand side we get lambda and the dot product. The right-hand side is mu, the dot product. Let's move the right-hand side to the left-hand side. Then we get lambda minus mu, dot product equal to 0. And we know lambda is not equal to mu. So the bracket is non-zero. It's non-zero, and that means only one thing. The dot product is 0. For a matrix to be diagonalizable, it needs to have n real eigenvalues. And that's indeed the case with the real symmetric matrices. This is what we are going to show here. The characteristic polynomial has n real roots. Matrix A is real, so its characteristic polynomial has real coefficients. So we can see that the roots of the characteristic polynomial, they are either real or in complex conjugate pairs. They are in pairs like this: a plus jb and a minus jb. But we want to show that all the roots are real, right? So it does not have roots of this form, only real roots. So let's start by assuming that we have a eigenvalue, lambda, and f of a of lambda is equal to 0. And this lambda may be complex, but we want to show that it's real. And v is an eigenvector corresponding to lambda. Another problem is, how can we use the property that A is symmetric to show that this lambda must be real? Alright, lambda is an eigenvalue and v is an eigenvector, so AV is equal to lambda v. And now we want to show lambda is real, right? So let's try to take conjugate of both sides. We take conjugate of the left-hand side and conjugate of the right-hand side. By taking conjugate, we are taking conjugate of each entry of A and each entry of V vector. Now we get V conjugate. Lambda may be possibly complex, right? So V might be also complex as well. But A is real, so the conjugate of A is still A. And this is the right-hand side, lambda conjugate and V conjugate. Let's play the little trick that we used in the proof of a theorem, the previous theorem. We multiply V transpose to both sides, V transpose and V transpose. And now let's use the condition that A is symmetric. Then the left-hand side will be V transpose A V conjugate, V transpose A transpose V conjugate. And this term can be written as AV transpose, and this is equal to lambda V transpose. Now let's equate the left-hand side with the right-hand side. This is the right-hand side here. Then we get lambda V transpose V conjugate, and lambda conjugate V transpose V conjugate. Both sides have the dot product of V and V conjugate. Then combining these two, we get lambda minus lambda conjugate and the dot product. We want to show that lambda is the same as a lambda conjugate, right? So if we can show this dot product is always non-zero, then we are done. So let's look at this dot product. V transpose V conjugate is V1 to Vn, and then V1 conjugate to Vn conjugate. Is this product always non-zero? We multiply it out, we get V1 conjugate. So this is V1 absolute value square all the way to Vn absolute value square. So this is always greater than 0. And this shows lambda is the same as its conjugate, so lambda is real. Now the main result. A is an n by n matrix, A transpose is equal to A is symmetric, if and only if there exists an orthonormal basis for Rn that consists of eigenvectors of A In this case, there exists orthogonal P and diagonal D, so that A can be written in this form. So whenever A is symmetric, it is always diagonalizable, and remember the diagonalizable result is P, D, P inverse. When we talked about diagonalization in chapter 5, we have P. The P matrix here is an invertible matrix, but with symmetric matrices, this P matrix can be chosen as an orthogonal matrix. This is an orthogonal matrix, so the inverse of P here is P transpose. So not only the eigenvector of A form a basis for Rn, it's an orthonormal basis for Rn. This is an if and only if result. Which direction do you think might be easier? Well, this is a very lengthy description, so let's say if this will be easier, if we can show that A transpose is equal to A from here. Let's start with this direction. We already know that PA is equal to PDP transpose. P is orthogonal. Now let's see if A is symmetric in this case. We take transpose of both sides. Then we get P transpose transpose here. D transpose is still D, and then P transpose. Voila, we get back A again. So this direction is not too bad, but I'm afraid that the other direction will require a lot of work. For the other direction, we want to show if A is symmetric, then there's an orthonormal basis for Rn that consists of eigenvector of A. And in this case, we can find orthogonal P, diagonal D, so that this is true. We know when A is symmetric, it has n real eigenvalues. Let's say lambda 1 is one of the eigenvalues, real eigenvalue, and V1 is an eigenvector corresponding to lambda 1, and V1 is a unit vector. Let's extend V1 to an orthonormal basis for Rn, V1 to Vn, and put these vectors in one matrix. This is Q, it's an orthogonal matrix. Now let's consider the product Q transpose AQ. We will see in a minute that this matrix has some very special property, and it will help us to see why A can be diagonalized. First, let's look at this matrix and see, would this matrix be symmetric? It is indeed symmetric, right? Because the transpose would give us Q transpose, and AA transpose the same as A, and Q transpose transpose back to Q, so this is indeed symmetric. Now let's look at the first column vector of this matrix. We only want to see the first column vector. We multiply with the E1 and QE1. Remember, Q is this matrix. The first column vector is V1, so QE1 is V1. V1 is an eigenvector with eigenvalue lambda, so let's plug that in. And remember, Q transpose. This is Q transpose, V1 transpose, V2 transpose to Vn transpose. So we are taking dot product of these V vectors. The first one, V1 transpose V1, that will be 1 because V1 is a unit vector. How about the other dot product? They are all 0. So the first column vector is actually a scaled version of the first standard vector. So here is how Q transpose AQ will look like. The first column vector is lambda 0, 0, 0. How about the row vector? Also lambda 0, 0, 0, right? Because it's symmetric. And this matrix, this submatrix down here, we call it A m minus 1 because its size is 1 smaller. Its size is m by m minus 1 by m minus 1. And it's symmetric. So what have we done so far? The only thing that we did is that suppose that V1 is a eigenvector, and we extend it to an orthonormal basis to get this Q matrix, and this Q transpose A Q matrix would be of this form. It's lambda 0, 0, 0, 0 on this side, and here we get a smaller symmetric matrix. And we are one step closer to diagonalization because you see the first column vector, first row vector here is the form that we would like to have in a diagonal matrix. Now that we have a smaller symmetric matrix, A m minus 1, then we can repeat what we have done in the previous step. So what have we done so far? First we find an eigenvector of A, we extend it to an orthonormal basis, then we consider this product Q transpose AQ, then we see that this Q transpose AQ is of this form. The first column and first row is like a diagonal matrix, but now this bottom right corner we have a smaller symmetric matrix. Let's call this process the star process. And we can repeat this star process on this smaller symmetric matrix. We can find orthogonal matrix Bn minus 1. We call it Bn minus 1 because its size is m minus 1 by m minus 1. It's an orthogonal matrix so that B transpose AB is now of this form. Again, the first column vector, first row vector are like that of a diagonal matrix, and in the bottom right corner we have a smaller symmetric matrix. If we continue this process again and again, then we can expect that eventually what we would have on the left hand side would be a 2 by 2 matrix, and on the right hand side we would get a diagonal 2 by 2 matrix. It seems now we are very close to our final destination, just one step away, because now these matrices B are of smaller sizes. And remember, what we would like to diagonalize is the original m by n matrix A. So let's try to construct m by n orthogonal matrix from these B. We call Qm minus 1. It's 1, 0, 0, 0, 0, 0, 0 in the first row, and bottom right corner is Bm minus 1. And Bm minus 1 is orthogonal. Would this Q matrix be orthogonal as well? We can verify this very quickly by forming the product. This would be 1, 0 at the bottom, 1 and 0, and row vector, 0 row vector, and this is B m minus 1 transpose, and then Q, and this becomes 1, 0, and 0 here, and at the bottom right corner we get B transpose and B. So we get identity here. This Q, n by n Q matrix is indeed an orthogonal matrix. Now let's add Q n minus 1 transpose Q n minus 1 to the product that we already have. This product here in the middle we know is this matrix lambda 1, and at the bottom right corner is A n minus 1, and Q n minus 1 definition, Q n minus 1, this is a transpose, and then the middle one is the same here, and we see they are all of the same partition. They are all block diagonal. So if we multiply it out, we get lambda 1 here, and now at the bottom right corner we get the product of this one, and this one, the three sitting here. We already know what these three together would be. It's this one. We plug it in, then this matrix here would now be replaced by lambda 2, 0, 0, 0, 0, 0 on this side, and A n minus 1. And now we are one more step closer to diagonalization. And the matrix that we have on the two sides of A are again orthogonal. This product is orthogonal. If we continue this process, we continue to construct Qn minus 2, Qn minus 3, all the way to Q2, then we will get a diagonal matrix on the right hand side. And if we call this product, this big product, P matrix, then we get P transpose AP equal to a diagonal matrix. Calling this diagonal matrix D, and multiplying both sides by this side by P and this side by P transpose, then we get A equal to P D P transpose.